Swayam Prabha. Digital India. Educated India.
Hello everyone. Now we will continue with the numerical calculations based on standard error or standard deviation. So basically we are discussing the sampling distribution. So next example is that the standard error of mean of yarn A is given. So one standard error is given, and then standard error of mean for yarn B is given. So there will be situations that normal situation is that your target value is given, suppose x is your target, and what we do, this is the nominal value, and we are producing in production, we are producing xp mean value, x bar p is target which is nominal we are producing, and we want to calculate the whether this difference is existing or not. That is one aspect. Another aspect, suppose two machines, they are producing two different products. So same product but two different values we are getting. So machine A and machine B. So in normal, when target is there, yeah, nominal value is there, in that case what we use standard error of mean, because where we have only one standard error will be available, where the distribution of the nominal value is not available, it's only a value, target mean is available, but its standard deviation and all other parameters are not available. In that case we use standard error of mean, which we have already discussed. But in the present case, suppose you have two machines producing a particular yarn. So yarn A and yarn B. Yarn A has got certain mean value x bar A, yarn B has x bar B, standard deviation A and standard deviation B, and number of individuals say in A and in B. These are the data available. In earlier case, this data were not available, only the target value was available. For that we calculated the standard error of mean. But in this present case, two entirely known individuals are there. For that, the calculation of standard of error to know, to judge, to know the difference, significant difference is there or not. So in this case, what we have to do, we have to use a term in place of standard error of mean normal case, difference between the mean, it's a standard error of difference between the mean, which is denoted as standard error difference. It's a not normal standard deviation, standard error. So in this type of numerical, to solve this numerical, we can calculate the standard error of sample A, ACA, and standard error of sample B, ACB. So, because we have the data of standard deviation is given and number of sample is there. So, standard error of A will be from the earlier and standard error of B number of samples. Now, here one thing we should understand. So, in our that equation relationship, standard error is standard deviation of population by under root number of samples. Standard deviation of population by under root n. Standard error of mean But if you don't have the population data, so what we do for simplification, what we use, we can use the standard deviation of sample also. So, this, if the population data is not available, we use this standard deviation. So, but these are the individual standard error. But what we are trying to get the difference between two set of data from machine A or data from machine B. In that case, we don't use normal standard deviation, standard error. Here we use the standard error of difference in this. Now, in this numerical is the first step towards that, where we want to calculate the standard error of difference. This standard error of difference will be used for actually calculating the difference between two set of data. Now, the relationship is very simple. It's under root AC1 square by AC2 square, and it's nothing but under root 4 square, 16 and 36. So, the standard error of difference will be 7.21. For yarn A it was 4, yarn 2 it was 6. So, standard error will be of difference will be more than that, because the individual data, this has got some variability, and between this also we are trying to know the variability. So, it will be added in square, okay, and then under root the added value. So, similar problem here, variance of population is 225, standard error of the sample mean is 2.5, number of individuals. So, variance means standard deviation square, which is 225. So, standard deviation will be under root 225. So, which is 15. Standard deviation is known and standard error is known. Standard error is given 2.5. So, we can calculate the n value from the relationship. So, standard deviation of population So it will be 2.5, this is 2.5 multiplied by 15. Sorry, 2.5 standard deviation is, population is, standard deviation is given. So n is the number of sample, n we have to calculate. So standard deviation is 15 and this is 2.5, and from there we can calculate the number of specimen. So for here number of specimen is 36. Now let us see if we have to reduce the standard error to say 1.5. So what will be the number of sample required? So to reduce the error, the population is given, population standard deviation is given. We want to reduce the standard of error. So that means 15 was the population standard deviation, 1.5 n. So n will be 1.5 by, sorry, 15 divided by 1.5 square equal to 100. So just from 2.5 to 1.5, if we want to reduce the standard of error, so we have to increase it from 36 to 100. So error we want, if we want to reduce, so we have to increase the number of specimen in a sample. Now next numerical is that 40 leaves were tested. So n is 40 and mean count x bar was found to be 50 and count CB is 2.5%. So what is CB percent? Coefficient of variation. CB percent is nothing but standard deviation by mean multiplied by 100. Okay. So here mean is given 50, CB percent is given 2.5. So we can calculate the standard deviation. So first thing is that we should calculate the standard deviation of the population. Okay. And here it is given 90, both 95% and 99% confidence level. So what it is asked, how many leads, that how many data point, how many strength, how many data Lee you have to test to reduce the error percent of both count and standard deviation of count to half of the present error. That's important, and that to both 95% and 99% level. So here we need two levels, 95 and 99, and number of test value we must calculate to reduce the error percent for both count and standard deviation of count. So the 4 different data are required. our results will be there. First, let us calculate the what is the present error percent for both count and standard deviation. First, let us do one by one. So, CB means standard deviation by mean into 100. So, from there we can calculate the standard deviation. It is coming out to be 1.25. If you see, this will be in the same unit. So, 1.25 is the standard deviation. We can consider it as a standard deviation of population. And what is the error percent? That we have already discussed earlier. In a sampling distribution curve, this is the sampling distribution curve, and here this point, say 1 sigma, 2 sigma limit, here T for 95%, say 95 into standard of error, that we have discussed. This is the error, that means deviation from the mean. This is the mean value, deviation from the mean. This is actually maximum error possible. So, that means T multiplied by standard of error. T into standard of error is the total error percent. This can go in plus side, this is called plus minus. So, plus minus T multiplied by standard error. It can be 95% or 99%. This is the error percent. That means this we can represent as deviation D. This error percent we have to calculate first. So, present error is that X. So, what is the error percent? So, we know we have standard deviation, we have number of leads, initial number of leads. So, from standard deviation and number of leads we can calculate the standard error. So, standard error we can calculate. So, standard error of at present, P is called present standard error. So, standard deviation by under root n. So, standard deviation we have calculated already. This n becomes 40. This is the present error value. Present error means here in this picture it is a D, deviation. This is the deviation here. Now, and this deviation is based on 40 readings. Now, what we have to do? We have to make this error half. So, new error will be, so maximum error, this is the standard error. Now, the maximum error is that, no sorry, earlier I made some mistake here, it is not error, it is a standard of error. Okay. Now, the maximum error X, which is D, has been given. So, maximum error as per this picture it is a D value, which is nothing but T into standard of error, which is written here. Now, what is the T value? We are dealing with here 95% level, and for large sample, it is a large sample. Typically in our textile material, depending on the variability, we consider 30, below 30 as a smaller sample, and above anything above 30 is a large sample, where we consider the degree of freedom as infinite, large sample. So this t value we have to get from the table, standard table value at 95% level. Let us see the table value. This is 95% level, and if we go down with the large sample, degree of freedom infinite, it's 1.96. So this 1.96 has come, this is the t value, and we get the maximum present error is 0.387. This is the maximum error. So this value, this d is 0.387. Okay. So this now the condition in our present problem is that we have got certain error here. This is the error we have got, error present dp 0.387 present error or x. Now what we have to reduce this error to half of the present one. At 90, suppose, then our distribution will be this. I'll change the color of the pen. The distribution for new normal distribution will be like this, sampling distribution, where the error is x new is half of x present. This is x new, sorry, x present error, x present is. So from our earlier discussion, we can easily make out that to bring this curve, present curve, to this stage, we need large number of samples. So that's how what we have to calculate. So next new error will be, so this is the t value, new error is 0.193. So for 0.193 is the maximum error. So we can calculate the new standard of error based on that 95% level. Standard of error we have got, which is 0.0984, and through the standard relationship, this is the standard deviation of the population will remain same, and we will get the new number of specimen required. By solving this equation, we get the new number of specimen is around 1.161. That means earlier it was 40 readings. So to make the error percent, to reduce the error percent to half, we have to increase the number of specimen in a sample. We have to test more number of sample. This is for 95% level. Now let us see for, this is for mean, and now in case 2, 99% level, similar treatment will be there. Again the standard deviation will be 1.25. Present error we can calculate, it is 1.197. Same, and maximum error, sorry, present standard error is this 0.197 standard error of population. Earlier case it was 0.197. Okay, so standard error of population will be 197. Only difference will be that when it's we are increasing from 99 to 95 to 99, that means the level will be changed. So the same formula, maximum error at present will be T into standard error at present, and this T value at 99% level, it is a 2.58. This we have got from the standard T table, and if you consider that 99% value, it is a 2.576, it is typically around 2.58. We can consider it as a 2.58. So this 2.58 we considered, and standard error value, so it is error is 0.502. Now new error will be, so earlier case the error was lower than this. Now new error is half of that, 0.254. From there we can calculate the standard error of mean for new standard error of mean. Okay, and this standard error of mean means standard deviation by under root n, and from there we calculate the new number of specimen required at 99% level. So interesting, you can see whatever may be the level, if we want to reduce or increase the number of the error percent at different level also, you need the same number of specimen. So these are all for mean. Now try to see what happens in case of the standard deviation. Here it was, the question was that both count and how many lists must be tested in order to reduce the error percent of both count and standard. Till now what we have discussed, the for count. For standard deviation only one difference will be there, standard error. Now please try to tell me what will be the standard error of population, standard error of standard deviation of population. So this is the standard deviation by under root 2n, under root 2n. So 1.25 by under root 80. The value becomes 0.139. So for standard deviation of mean was, standard error for mean was 0.197, and for standard deviation it's a 0.139. Okay. Now maximum error will again be x, standard deviation error will be 1.96 multiplied by 0.139, 0.27. So 0.27 is the maximum error at present. Now the maximum error new error for standard deviation will be half of this, half of 0.27, 0.136, 0.136, half of this. Okay. Now if you see here, the standard error, this is the value, standard error new standard. What was the standard new standard error? New standard new error is this 136, and standard error was 0.139. 0.139 was the standard error and 0.136 is the new error. So 0.136, and this, what is the value? This value, this is the 1.96 multiplied by standard error new, standard error new, standard error new will be 0.136 divided by 1.96, 0.069. This is the standard error of standard deviation, standard error of standard deviation. Now standard error of standard 0.069 equal to standard deviation of population was 1.25 divided by under root 2n. So under root 2n, 1.25 divided by 0.069 2n. So 1.25 divided by 0.069, 18.11. So 2n will be 18.11 square three two eight 328.1. So n will be 164.05. Okay. So effectively it will be almost same, because here the calculation it is coming, this difference is coming because of some rounding off at certain point. Ultimately we'll get around it. Here rounding off is there. So what we are we can see, being it standard error or standard deviation or mean, so the number of sample, if you want to make it half, error is half, from 40 you have to increase it to 161, around 161, and that too both 95% and 96% level, the result will be approximately same. So one can recalculate it. Now the first objective of this is this whatever we have done till now, it's a basic understanding before we do the sampling analysis. Okay. Now the significance test, because we have discussed there are two objectives of sampling analysis. One is the test of significance, another is the confidence interval, confidence level. So test of significance is that here, which is the first objective. The significance means that our basic target data is this target value, and we are achieving this value. We have to see whether this difference D is there is a real difference is there or not, that we have to judge, and this is called test of significance. Okay. Now how will you judge? So there must be some reference value of this difference. We will calculate the value, we will get some difference value, some error value, but this error, whether this error is okay or not, that we don't know. So someone should tell me that what is the point, this D value we are getting, D is say 5, this 5 error is okay or not, that is not clear. So for that we need some reference value. A reference value of this variability, this D is not available, because it depends on the population, on the type of population, on the variability of population. And this D, what is this D? D is the T times of standard error of mean, or standard deviation, whatever. What is this standard deviation? As we have already discussed, that standard error depends on the number of specimen we are taking, or the variability, the standard deviation of the population, how much the population is varying, the data is varying. So this is the sample specific value. Standard error is the sample specific value. So there is no, you cannot target, but T is the value which is basically it is some standard value. Like in normal distribution, we saw 1, 2, 3. These are the standard level. T is the also a standard levels are there, and T is this level is this T value is available for different levels of confidence. So for higher confidence, if we want to have higher confidence, so this is the T value here. For T value, say 95% confidence. 95% confidence means you are actually, your assumption will be true 95% time. Okay, 95% time will your data will be within this zone. Only 5% time you are missing. So that's why it's called, sometimes it's called 5% level. 95% confidence. So that is the term. And if you want to be more sure, this will be 99%. So two levels we will be discussing. Here T value will be for same distribution, same sample, the T value will be more in case of 99%. So we call it as T99 or T95. So T99 and T95 are available in a table form, standard table form, and based on our present distribution, we can also calculate this T value. So our calculated T value and table T value we can compare. If the, suppose this is the table T value, and if our calculated T value is less than this value T value, then the, and significance test, what we are doing, we have to compare with the mean value, standard, central value. So from the central value, if the T value is less than this, that means the data will be lying on this. So the change, the difference is not that significant. For 95%, and if you want to have 99% confidence, and the difference, so T calculated, so you are then you are comparing with the calculated T value. So in that case, T calculated will be less than 10. If it is there, then we can call it at the difference, whatever difference is there, it is not significant. As I have already mentioned that our target is say 50 English count is the target value, the nominal value. It's not possible to achieve always in at 50. It's not, either it will be more or less, coarser or finer count, or strength may be higher or lower. We have to judge whether this difference is significant or not. If it is not significant, we should not bother. Now this is 95% level. There is always confusion comes. 99% level means more confident, higher confident. So why is it more than that? Suppose my data is here. That means both in 99% confidence or 95% confidence level, this is always, it's not significant. But if it is there, that means 95% confidence limit, it's more, it's a failing. But 99% confidence, it's because when you increase the confidence, if you want, because we are not increasing, we want to be confident that my data is lying that. If we want to be more confident, that means range has to be more. Okay, that, see, if I have, I'll tell you simple example. Suppose in a football, in a football, I have a bar post of this size. I am shooting from this point. Okay. So out of 100 shots, there may be 5 miss. Okay. Now, if I want to be sure that out of 100 shot, I want to score goal 99 times. So your bar post should be little bit larger or smaller. It will be larger. So higher size, within that zone, you are trying to be more sure. Okay. So steps are that first you calculate a t value using appropriate formula. There are formulas available for calculating t value depending on different conditions. So this t value calculation we will discuss. This t indicates the position of the actual value, the sample, as compared to the idealized value. Idealized value is this, and this is the table t. Your t calculated t comes here, suppose, actual position. If, and then you are comparing with the table t value. So you must remember this t value which we are calculating is indicating the position of your reading, mean value. Now, if the d is higher than the standard tabulated value, effectively t is higher than that standard, because standard error is same. If t is higher than the standard tabulated value, then the difference is significant, or vice versa. AC is calculated based on the actual data unique for a particular sample, that I have already mentioned. So this AC should be, it depends on the particular sample. We are calculating the AC value, and calculated t value is compared with the table value. So you see, this is the table value, and here in the vertical form it's a degree of freedom. This degree of freedom is basically, it's a n minus 1 that we have discussed, number of specimen and minus 1. Okay, that is a degree of freedom. And as I have mentioned, for the other type of material where variability is different and also the accuracy required is different, in all those cases we can go on taking the different degree of freedom, different number of sample specimen we use, and for say for 60 degree of freedom we can get the t value for 99 and 95% level. But for textile material we generally assume that 30 number is the large sample, where we consider the degree of freedom as infinite. So first objective was that we want to be sure that whether the difference is significant or not. If it is not significant, then we should not change our process, and which will not, it's not going to affect the final product. Like 50 any yarn is there, your target is 50 any, your buyer has set, I want the 50 any yarn. Now what you are producing say yarn of this is 50, 50.5, 50.5 is coming here, so which is within that acceptable limit. So we should not bother, we do, and we should not target also to produce 50 any. Now it is say 51 at this point, that means it's a crossing the 95% level. Crossing 95% level means whether should we take action or not. Sometimes we don't take action, it's a warning, but when it is crossing say 51.5 at this point, then it's basically significant. So 95% significant level, if we cross 95% significant level, sometimes we take, okay, we see that there is an evidence that there is a difference is there, some evidence is there, there is a difference, but it's not that significant, we don't take action. But when it crosses 51.5, that is 99% level, in that case we should stop the machine and readjust the count, yarn count. So 95% confidence levels, we sometimes tell, okay, there is a error is existing, but we should avoid. Now what does it mean? So if you produce 50.5 or even 51 count, ultimately if you mix it, the yarn bobbin you are going to mix, that will not actually affect significantly in the final product. But when you are mixing the 51.5 count and in the another side the says 50 count, then there will be a problem. It's not acceptable, because 51.5, so that means 50 plus 1.5 count, 50 minus 55 minus 1.5 count, it will be 48.5. So your range is 48.5 to 51.5. Within that range, if we allow the material, it will give some defect in the ultimate product. And second objective was, a sample can give some information about the whole population, but it cannot give the complete information. Like our target was 50 any, 50 any, and we have got say 1 million bobbins, 1 million bobbin, and our basic target nominal count is 50. We have got say sample of 20, sample of 20, and what we have got, we have count is coming out to be say 51.5. This is the target given. Here it is target given, but suppose you don't have any total population, you don't know. Target is given, but total whole population you don't know. 1 million bobbin, we don't know what is the actual value. What we are trying, we have got 20 readings, 20 sample, we have got 51.5. Now overall population Whether it's 50 or not, we don't know. Whether it's reaching in that range, we don't know, but we have to, because we have tested only 20. So from 20 sample, 20 bobbins, we have got 51.5, but through this sample analysis, we can get some range, maybe say 49.1 to say 52, 52 point something, within this range. Within this range, when we are talking, and this range is called the confidence interval, and with that range we can tell, say it's a 95% confidence level, we can tell, I cannot tell that the mean value of the population is 51.5, but I can tell that mean is lying within this range. Mean is lying within this, that is the confidence which at with 95% time my assumption will be correct. That means by simply testing 20 bobbin, I cannot tell the exact value of the mean, but I can tell that my reading will be actually the mean of the whole population will be within this range. Now if I want to be more sure, I want to be correct 99% time, as I have told, given example of bar post. So I will increase this range to little bit, 99%. So I can go on. So this range we are going to calculate, that is the second objective. Hence the mean and standard deviation derived from the sample will only be estimate of population. This is whatever we are getting, mean or standard deviation, these are the estimates, estimate of the population. It's not the actual population mean. This, but this estimate has to be some confidence. We express the estimate in the range with a certain degree of confidence. So that range is called as confidence interval. So this confidence interval is extremely important, and which we can get from the sampling distribution, because only by testing 10 or 20 sample we are getting certain value, certain, actually we are projecting the value of the population within short time. And if we want to be more sure, we will increase the number of samples, so confidence will be more. So for this confidence interval or significance test, we use different types of tools, and these tools we will discuss in the next class. Okay, till then, thank you.